ஹலோ ஃப்ரெண்ட்ஸ், நான் ஜஸ்டின். நம்ம இன்றைக்கி எங்கே போகிறோம் அப்படின்னா, இந்தியாவிலேயே நம்பர் 1 இன்ஜினியரிங் இன்ஸ்டியூட்டுக்கு தான் போக போகிறோம். ஐஐடி தான் போக போகிறோம். வாங்க போகலாம்.
Just so that this is in time, and we measured around 60 seconds, and this is in volts actually. So this volt will be proportional to the displacement. So there will be a conversion factor between the because you are recording using a photodiode, right? That photodiode will always give you volt, and you should know what is the conversion between this volt and nanometer. So there is something called calibration factor that we can measure from the basic experience. So if you multiply, that's a constant always. So suppose it is 100, you multiply with 100, then it will be around 220 nanometer, 240 nanometer, like that. It will be in nanometers always, the displacement. So that's about optical trapping, optical traces and optical trapping. So we do a little more experience. We are investing the setup on the fluorescence, the collecting fluorescence, not fluorescence microscopy, but collecting fluorescence lifetime measurements, like spectra measurements, like emission spectra. For example, this particle, I don't have the 980 laser right now. So if you use 980 laser instead of this 1064 laser, you are not seeing a laser here, right? But if you are using 980 laser, you will see this particle is emitting in all visible light. We can measure the spectra in the same manner. We couple that light to a spectrometer. We have a spectrometer there. We can measure the spectra. And if you want to measure the lifetime, fluorescence lifetime, how fast this lifetime is decaying, we can couple this into this is a lifetime measurement unit. We have an avalanche photodiode. So that is a photodiode which is highly reverse biased, which means if you have a single photon. So these are normal photodiodes, silicon photodiodes, which it has some cutoff, which means it won't work at very low intensity, which means it needs lots of photons to work. Like photoelectric effect is simply you are putting in some photons and you will get voltage. That is photoelectric effect, right? So there is something called avalanche photodiode. It is highly reverse biased, which means if you have only single photon, it will give you some voltage. Okay, so to measure the lifetime, you need when a photon is coming, right? When a photon is coming from the laser, so that time you can record. So that we have a setup there. So that's about this one. So that is the basic applications. And here you can see I am measuring XYZ translations, right? So these are called XYZ. This is called translation. So how, like if you want to measure the rotation, suppose the particle can have 6 degrees of freedom, right? See, 3 translation x, y, z and 3 rotational. 3 rotation means rotation about x axis, y axis and z axis. So these are called peaks, roll and yaw. So if you want to measure the rotation, so what will you do? So that is the technique our professor has developed here. So translation is well known. So optical tweezers they invented in 1990s. So from then everybody knows how to measure the translations. But rotations, how will you measure? How will you classify the rotations? And also if you see a particle here, and if the particle is rotating here in plane, you are seeing a plane, right? You are seeing a plane, and if the particle is rotating in this plane, then that is called yaw rotation. If it is rotating out of plane, that is called pitch rotation and roll rotation. So yaw rotation anyone can measure. So that is known, like for 20 years it is known, but the out of plane rotations were unknown. So our professor made a setup for that. For that, if you have a if the particle is rotating in out of plane, and it will have a scattered pattern, you won't understand much details of it, but I'm saying there will be having a scattered pattern like that. If you see 4 lobes, there will be 4 lobes like that. So that is from here, that you can get from here. The particle is scatter the laser, and if you cross the laser, if you take a, like suppose you are giving a polarized intensity, you are giving EX laser, which means your laser is polarized in X direction. You know, laser is highly polarized, right? You are giving polarized laser in X direction. Because of this rotation, there will be EY component in the output also. Not only EX, there will be EY also. But if you are measuring EY, you will see the 4 lobes like that, and from that 4 lobes you will see pitch equal to 0. The heading you just see pitch is equal to 0, or 4 lobes are equal, right? Intensity is same, right? But when pitch is equal to 30 degree, you see the heading in that blue figure. Pitch is equal to 30, the bottom 2 lobes are dimmer, right? Top one is brighter. So if you take a difference between the top and bottom half, you get some number, and that number will be proportional to the angle. And like that you can measure the rotations also. Translations is known, and rotations are just now invented. So that's what we are exploring here using this system, and for the bio purposes we are using that. So that's a more sophisticated one, and yeah, that's about this setup. So if you are studying human cells, you should keep the human cells in 37 degrees, right? So, and you are running on AC, and the atmospheric temperature will be different, and the temperature will be different. It won't be 37 always. For that, to maintain everything at 37, you have a temperature control here, and you can give you can give carbon dioxide. So carbon dioxide will ensure that the cells are staying alive. It won't die soon. And you can give humidity. Our body has proper humidity, right? You can give humidity by putting in water. All these are done by this machine. Okay. So this is your microscope, and there I am manually changing. I am manually moving the sheet. Here I have a joystick. I can play like this. Okay. So here here also you can see the particle, but you tell me which one was better, the previous one or this one. You have to focus it properly.
ಇದೆಲ್ಲ